In our previous lesson, in this series on sorting algorithms, we had discussed selection sort algorithm. Now in this lesson, we are going to discuss another sorting algorithm named bubble sort. So once again, let's say we have a list of integers given to us in the form of an array, something like this. Let's name this array A. We have 6 elements in the array, so we have indices from 0 to 5. Now we want to sort this array, so we want to rearrange the elements in the array in increasing order. What we are going to do in this algorithm is we are going to scan the array from left to right multiple times. We will call each scan one pass on the array. It's like we will first look at the 0th element and then look at the 1th element and then the element at index 2 and so on. Of course, we will not scan the array for no reason. What we will do is when we are scanning the array and when we are at a particular position, we will compare the element at that particular position with the adjacent element at the next position. So if we are at 0th position, we will compare the element at 0th position with the element at 1th position. And if the element at the current position is greater than the element at the next position, we will swap the two elements. In this case, 2 is not greater than 7, so we will not swap the two elements. We will just move on to the next position, which will be position 1. Once again, we will compare the element at this position with its next element, and if it is greater, we will swap the two elements. In this case, 7 is greater than 4, so we will swap the position of these two elements. So 7 will move to index 2 and 4 will move to index 1. And now we will move to index 2. The number at index 2 at this stage will be 7. Once again, we will look at the next element. It's 1. 7 is again greater than 1, so we will swap. And now we will move to index 3. Once again, at this stage, the number at index 3 is 7. We will compare it with 5 and we need to swap again. So 7 will go to index 4 and 5 will move to index 3. And now we will go to index 4. As you can see, this whole process is pushing number 7, which is the largest in the array, towards higher indices at each step. When we are at position 4, once again 7 is greater than 3, so we will swap. There is no next element for index 5, and at this stage we are done with one pass on the array. And what has happened after this one pass is that 7, which is the largest in the array, is at its appropriate position. It deserves to be at position at index 5 in the sorted array, and that's where it is. So 7 has kind of bubbled up to the rightmost position in the array with this whole logic of swapping the adjacent elements. This was our initial array, and after first pass we have gone to a state like this. If I quickly have to write pseudocode for a pass, it will be running a loop something like this. We will run a loop from 0 to n-1. Let's say n is the number of elements in an array, and if ai, the element at position I, is greater than element at position I plus 1, we will swap the two elements. There is one minor bug here. If I is equal to n-1, it will be the last index, so there will be no element after that. So we will not be able to access ai plus 1. So we will run this loop only till n-2. We don't want to access an index that will be out of the bound of the array, out of the range of the array. For I equal n-1, ai plus 1 would have been out of range. Okay, so this is the state of the array after one pass. What if we perform another pass and once again keep comparing the adjacent elements and performing swaps? If we will do so, now the second largest element in this example will end up at index 4. The second largest in the array is number 5. So after second pass, our array will be in a state like this. With every pass on the array will be divided into two parts. One part will be the sorted part and another part will be unsorted part. After two passes, the part of the array from index 4 till 5 is sorted and the part of the array from index 0 till 3 is unsorted. With each pass, the largest element in the unsorted half will bubble up to the highest index in the unsorted half. So in third pass, number 4 should bubble up to position 3, index 3, and while scanning, once we reach to the part where we are already sorted, there will be no swapping. we can actually avoid going to the sorted part. It will only improve our algorithm. To pass 3, our array will be looking like this. In fact, we are already sorted. In general, if we will conduct n minus 1 such passes for an array of size n, we can say something like for k 1 to n minus 1, or we could say for k 0 to n minus 2. After n minus 1 passes, we are guaranteed to be sorted. So this is our pseudocode for bubble sort algorithm. Given an array and the number of elements in the array, this function bubble sort will sort the elements in the array in increasing order. Let's now try to analyze the time complexity of this algorithm. The running time of this algorithm will be the running time of these statements inside the nested loop. Let's assume that these statements will take constant time c in the worst case. These statements will execute in constant time. Now the first loop will run exactly n minus 1 times, and the second loop will also run exactly n minus 1 times. So the total time taken as a function of n will be n minus 1 into n minus 1 into c, which will evaluate to cn square minus 2cn plus 1. Whenever we have a polynomial expression for time, then we say that the time complexity is big O of the highest order term in the polynomial. The highest order term here is n square. We just remove the constants and we say that this running time will fall into the class big O of highest order term. In this case, it will be n square. If you do not know about big O notation or how to calculate running time of algorithms, we have a whole series on time complexity analysis. You can find a link to it in the description of this video. Big O of n square is not the best running time for a sorting algorithm. In fact, this running time is bad. Bubble sort is a slow sorting algorithm. It's as good as selection sort, but both bubble sort and selection sort are slow sorting algorithms. We can do a couple of things in this algorithm to improve the time complexity, at least for some scenarios. The first thing that we can do is we need not run this second loop all the way till n minus 2 all the time. As we had discussed earlier, at any stage during the sorting, the array will have some part as sorted and some part as unsorted. There is no point passing through the sorted part because there will be no swapping in that part. For first pass, we can run this inner loop till n minus 2. For the second pass, we can run this inner loop only till n minus 3 and we will be good. For the third pass, we can only run till n minus 4 and so on. So in general, we can run this loop till n minus k minus 1. So when k is 1, we will run till n minus 2. When k is 2, we will run till n minus 3 and so on. This is some improvement. But in this case also, if you would calculate the time expression, it will be some polynomial of the form an square plus bn plus c. So complexity will still be big O of n square. We can do something else to improve this algorithm further. If you remember the example that we had picked up, it was sorted after 3 passes only, and 4th and 5th pass was only redundant. If the list is already sorted, there would be no swaps. So if we go through a pass without swapping anything, then definitely at that stage the list is already sorted. So I'll do something like this in this algorithm. I'll take a variable and name it flag and set it to 0 before making a pass, and once this condition ai greater than ai plus 1 is true for any I, then we will have to swap and we will set this flag as 1. And now when we will come out of this loop after a pass, if flag is 0, then there has been not even one swap. So we do not need to conduct any more passes, so we can break out of this loop, the outer loop, and this way we will avoid making redundant passes once the array is sorted. Now with this modification, if we input an already sorted array to the function bubble sort, then this particular loop will execute only once to figure out that it's already sorted. So the time taken, if we were considering this as taking some constant time c in the worst case, the time taken will be c into n minus 1 only. So this will be the best case for our algorithm. Our algorithm will be big O of n in the best case. In the average case, somewhere midway after making, let's say, n by 2 passes, we will exit the inner loop. If we will deduce the time complexity expression, it will still come something like an square plus bn plus c kind of expression. So in average case also this will be big O of n square, and in worst case the inner loop will also run n minus 1 times, and we will be big O of n square. Bubble sort is in place and stable sorting algorithm, and we just reduced its time complexity, which is big O of n square in the worst case. This is it for this lesson. Thanks for watching.